phase beacon chain, and then put all this data in other kind of instance. So you can do like this. So you have this data right here, and see more things about this base beacon chain and how the protocol specification about this way. So let's move to see what it's all about. And you can find the Ethereum specification that all the time have releases, official releases about the protocol specification. So this is a video for question and meaning, and you can find a lot of things here. So let's move to see more things about this kind of specification. So let's see the beacon chain. And see where is this beacon state. So let's see the beacon state, and we can find here all the specification. That it's a client beacon state. So let's make this specification here to understand all the things. So you have that it's a class, that it's a beacon state, have a container. So let's to see another file. Calling protocol specification.py. So you have here protocol specification. So let's start with this beacon state. That have this container, and you can put here all the data that you need. So if you start from scratch and you want to figure out what it's all about this beacon state, so you can find here all the conditions that the beacon state have. So the first implementation is the versioning that always have a genesis, that's a time. You can have the protocol specifications, what kind of genesis time do you want. In this case, you also have the genesis validators root that make a root. So you also can find here interesting ways to see how this is work. So I'll go to the Ethereum research hub page and find interesting way to figure out. So you have here, and you have the beacon chain implementation, that is the phase 0 the protocol, and you can find here the first script that start to think what have this block. So you can find here all the fields for this block. It's a class for a block, and this have a parent hash, kind of hash, a random reveal, that is the beacon randomness, a kind of hash, attestation bit max, that's segregation of bits, and the attestation aggregate sync. So these kind of things happen when the chain start to make the first cross links and have this slashing condition. So it's the way that the protocol starts to do the good shit. So then you have these shard aggregate votes. So these aggregate votes start to validate the shard chains and the shard blocks. So you are out there, you can ask me anything in the comment section. So let's move to see more things about this block. So you can find that the fields are the parent hub, the skip cube, the random reveal. That is the banker, the beacon randomness. That is all about the rundown and the BDF meaning, and that it's a interesting way to see make inputs random for extra layer of security. You also have the shard aggregate box, and then finally you have the output that you need, that is signature of this. And this kind of protocol wants to use the VLS scheme. So VLS is interesting signature scheme out there, and the way that they make the signatures provides a better security in so many ways. So let's move to more code here. We can find here the first things of this beacon state, and it's particularly equal to this crystallized state, because you have these active validators, quit validators, exit validators, and the current. So the beacon state go to crystallize when you start to make the validator records. So you start to sharing a lot of data in the attestation and the crosslink meaning. So it's a way to start to understand how this protocol connect with the data. So let's see here more in the beacon state. So let's find other in the Trinity repository for find this beacon state work properly. So let's find the beacon state to understand the things about this protocol. So have the beacon state in a block handler, the tuple of the beacon state and simply the beacon block. We also have the beacon state in the epoch processing. You also have the beacon state in the beacon operation of the block. You also have the beacon state in process the block header, because it's how the block header is connecting the chain of the beacon chain. You also have the types of this, how to process the beacon state. You also have here the precision processing of this beacon state. So under the hood, you can start thinking in this beacon state in the things that you want. So you have the genesis state. So from the scratch, start to make this script and make the things of slashing things, slashing specification. So let's start thinking the other condition. So maybe you want to make this script so long. And so the things that the beacon state needs. So this beacon state needs the slot that is the place that we all occur in the attestation meaning. You have the fork, but we have variants of this kind of things, so you need the story of this. So you need to have the block header, the beacon block header. You also need the block roots, the vector, need the root, slot, per historical root. You also need the state roots. That also is a vector. You also make this. Remember that the slot is it's where all it's happening. The meaning of connect this beacon state with the other state. So far you can find here all the data that this beacon state have. Then with the story, finally find historical roots. Can make a list of these. You have the roots, historical roots, limits. Then you have the 81 data, it's the proof of work chain, and you have the one data. So you need to make a registry for this data that you are having. So let's see another way to see this. So you also have this data that is the thing. You have always this object that is the data of the votes. That is a list of the one data, and the box per x will be the thing for understand how to enable this voting period for a slot per epoch. Then you have the one deposit, because remember the way for make this data, this new data, it's in not hard fork, so you have different way to see. So it's a good sense to replicate this protocol specification to understand the beacon state. So you can find here in the way that this beacon state make all the things, but in different ways. You have the commit helper of this beacon state. You also have the aggregator of this beacon state here, and you can understand that this is the protocol specification to make up the better performance that you could have. You have also state transitions. It's interesting to see how this beacon state in the chain. You also have here the validator, meaning that's all. So beacon state. You also have the pretty in Genesis. So beacon state. Constant of the Python meaning. Base of the Python. You have here the scoring of the fortress rule. That's a way to understand how this beacon state starts to connect with the shard blocks. And you can find here how get this stable root. You can find the protocol specification out there this way. Have the block roots of the vector or the slot for historical roots. So it's another way to see how to get this kind of protocol. So also you can find that it's the way to understand then the crystallized state. That could be the phase 2, phase 1, maybe of this kind of protocol. So you have the crystallized state and you can start thinking how this current block that you are connect make this next shard. The next shard, the signal for the crosslink will start from this kind of protocol specification. So you can find how this beacon state make the longest chain rule for understand the things out there. So it's an interesting way to see this data is started to connect in so many different ways. Okay, so far we saw here the beacon state, and we can find that we have the Genesis time, the Genesis validator, yeah, we have the slot, that is the thing that you start to connect in this way. You have the versions of the variants of this that is calling fork. You also have a story protocol specification that will work in different ways. You also have the slashing condition and the eth1 data, that's the how this proof of work chain start to get data for the beacon state. Because remember that the way this beacon state start, it's about a deposit contract. So let's move to see more things of the beacon state protocol specification to understand things that the container have. So let's see here that this is another way to see how this shard start. So let's move to see this beacon state. And we can have here how this beacon block, that it's also the beacon state itself, have to sync the beacon block. You have the signature in the scheme, this scheme is different, you can find it there. And you also have the helper functions of this. Okay, so far we can find that we have the single beacon block and the single beacon header. So it's the two ways to see and understand how to make the signature in this way. So let's move to see more interesting. For example, we can find here how this signature wrote in this protocol specification. So let's see things about the beacon state, because it's the thing that we are talking about right now. So let's see the latest block header. that is how this beacon state is connect. So let's see in the protocol specification. And find out how to connect this. So we can find here that it's all about the lattice processing. So you have the statement of this state that if the lattice block header with the state root have this kind of hash, this state transform the lattice block header. So you can find here the story that it's about the protocol specification out there. So you can find here lattice block, interesting way to see. And you need a specification about different objects. That kind of objects could be denting in the crystallized state. That would be in codes because it's a non-term crystallized state. Because we need to find the next shard and the crosslink it's the way to get the next shard. So let's move to see more about this lattice block header. That is the protocol specification, and we can find more about this code. So you have here the beacon lattice block header. So the slot, remember, is where it's all happening. So it's important for the protocol specification because it's the thing that the beacon randomness need the input or outputs between the rundown and the PDF make a good sense for this kind of way to see. You also have the Genesis Pi, that's the lattice block header, that have the beacon block header, and create. So you also have the body root, that's a beacon block body, and create the hash tree root. Okay. So far we have six kind of implementation about the beacon state, and we have similar way to see the lattice block here, that it's all about how to connect the slot with the block and create the beacon block header in the parent roof for that kind of block. Because remember that it's all about the height function that in the Casper basics that we saw in that paper, we can figure out how to connect this block header with the next block header and start to make these shard chains in the longest chain rule. Let's move to see more protocol specification about this topic. So let's see the block roots. And find out what it's all about. So we have here the block roots. That is a field for the historical batch. and these block roots always have a sequence. So let's copy this to understand the basic of these block roots. So you have block roots here, make a comment, find a better way to understand these block roots. So these block roots have the sequence of the root that is a default tuple. The way that it's connect the other kind of protocols out there. Let's move to see more of these block roots. That is a protocol specification of the beacon state. This is an interesting way to see how it's working. You can see the vectors. These you have white, 52, and there is a lot of code. Have the way that will be serialized, that is they call it this CCZ vector, and it's an interesting way to see how serialized data. And the slot processing. So you also have this way that could be the state of slots. And it's an interesting way to understand how these block roots means for the protocol specification. So vectors and the meaning of serialized state. That could be CCZ way. So then you can find here all these protocol specifications that are the block roots. Let's move. You can find 2 pages of this data. If you have any question, you can ask me anything in the chat or in the comment section. So it's an interesting way to see how these block groups works. But the principal way to see these block groups is the block groups is a sequence of these roots and have this default tuple. Because in the protocol specification you have this vector of this sequence, and this sequence could be this way to understand the protocol. Slot for historical root. Because remember that in the slot is where all is happening in the protocol meaning. So understand that sequence is equal to the slot or historical roots. So you can understand here how this data make these historical roots. So you have here the genesis state, that is the first beacon state, and start to growing in the longest row. So it's interesting to see this historical context in the beacon state. So let's refresh this. So this is the genesis state. So you need to start to dig these blue roots, that is the sequence for the roots, and have this default tuple that the sequence needs to start digging the slot for historical root. So makes sense in the discrete math. and this start growing in the longest row with the genesis state that we need. So you want to make your own PFT protocol and you start to figure out how to connect different states. This kind of open source code could help a lot in your research because the BFT protocol doesn't only have a meaning in the blockchain context, also have in a different kind of softwares. So these kind of softwares are very interesting how this historical slot start to make sense. So let's move to the code to see more things about this protocol specification about this beacon state, that is how this data starts to make sense in getting from 8.1 data that is calling that in the protocol specification. So let's see more things here. And we have another interesting thing, that is the registry. So let's move to this thing, registry. So there is when the validators start make the things. So you have this validator and this validator registry has a limit. So this is a good protocol specification to understand. And you can find in the research full proof of stake that was the first script in Python, you can find here about this kind of protocol specification of the way that the validator starts to sync. You can find here that a verified it's a way to make this object to make the thing that you want that is verified, and always you have this tricky tuple. So it's interesting to have this limit in this way. So you can find here that limit is a good spec for protocols with different chains out there. So it's a technical way to see how this makes sense in the longest chain row. And also you have the height function that it's the way to protect these validations. So let's move to see more about this registry. So it's blockchain, so you have the balances. And these balances is a list of the way that it's the unit and of Ethereum per gas, that is the principal protocol specification about the virtual machine replication. So you have the validator, registry, limits. So let's see more in the Trinity client how this works for the kind of registry, this kind of data in the side of the validators. So let's move to see interesting way how this is work in the protocol. So you have this validators thing. So you have the validators and you start to thinking in the state of these validators. You have different objects here that is a sequence of validators. So these sequences, it's a sequence of validator meaning. So it's not the only sequence that you have. If you remember, we have here another sequence. that is the sequence of the roots, and this makes sense because you have to connect all the beacon state with the shard chain. So it makes sense in that way to have right now in the protocol specification the validator side of this approach. So you can see that it's a huge amount of code out there. So this sequence of the validator make this thing for start to make the statements that other things in the protocol specification needs. And so far we can find the Genesis validator that needs to run and verify this index export, and you have this condition that is the slot per epoch, the max validator per commit. Another interesting way to see how to reach the consensus. So these implementations are very technical way, but have a very good performance. So far you can find all the things about this validator side in the protocol specification of the beacon state. So you can find different ways to tricky this variable in your experiment. So you also have here for example, this one. It's a very good night. So it's a test. Let me see. This is the thing that you need to serialize in the vector that you want. So let's move so along this code to see more interesting. You need to run the beacon nodes. So you have the cryptographic primitives here. So we have here to block validation. And let's replicate that data to understand the sequence of validator meaning. So you have the proposer. Let's put the proposer index, and you have the get become proposer index. So you have the state and the config of this beacon state. Then you have the proposer, that is the state, and the validator side of this canon data. So you have the proposer index. So it's a very good way to see this script, how this start to work. So this is the side of the validator. So let's copy for a good recommendation, the kind of protocol that you want to make in another way. Let's move to see more interesting things about this validator side in the beacon state. Because we saw that it's a proposer state and needs the index way. So this index way, we can see that you have the index for E, you have the index of something that have the indices. So it's an interesting way to see how this is working. So let's move to see more about this validator side. You have a key, you have here the epoch process helper. That is the way for this state validator have the current epoch. And you have more data here, that's interesting why for the Python object meaning. And of course the fortune rules, that's all about the scoring implementation. You have the test code. Let's move to see more experimental code about this beacon state in the side of the validators. So you can find here more things about the validators, how this data works. Okay, you can find here the protocol specification. You could find work in a good sense for the things that you want. The protocol specification that you want to one build. So let's pay and see that is the max validators per commit that needs to be a good way to make a better protocol specification here. Let's move to see more interesting way here. Let's move to the 7. And so the components, and you can see here that it's in a better way to find here in the way of the int to understand how this works under the hood. So you have the condition of the protocol specification here, and you can start to play a little bit about this, because remember that the Byzantine fault tolerance protocol are not so friendly. It changes variables of how this consensus works, so it's so hard to understand how to get a transition of this consensus meaning. But let's move on different things about this kind of approach. So, for example, we have a very good, nice thing here. Let's to see that it's the fortune rule that is about this current thing that this beacon chain start to make for growing in the longest chain rule and make interesting things. So you also have here different problems. It could be the data availability problem, because you have different ways to need to compare this data with the other chains. So you need to figure out that kind of stuff. Let's move to see this. So you have here the LMD ghost, and we can find here that it's a script that works in the meaning of a score, and this score is like a way to make the last test at the stage imbalance and the score by blue row. So see, if you want to understand more the LMD goes, you need to deep dive, a very deep dive in this kind of protocol that is the Casper the friendly ghost. You also need to understand the way of the Casper basics works, that is calling the Casper the friendly finally gadget, and of course you can find out there the adaptation of this protocol, that is the Sound-Volosky thing that it's calling the really heavy observer sub-tree that it's calling us, and you can start to understand the way of the host works. But let's move to the code. So okay, you have this implementation of the ghost, but I have this variant of the meaning that have this score, and this score works for make an extra layer of this security. So if you don't have this score, only works in the meaning of Act sub 3, Hibis 3, Hibis sub 3, so have a different approach. If you make a better security in the way of how this protocol is connected, you can make this variant of this protocol that could be a score. So, for example, if you have a Byzantine fault tolerance protocol and you want to make extra security for this, you can implement this way of scoring the things, because this scoring things works in a tuple. In this tuple, in the object, you always have the weight that you want for the protocol. So it's a tricky way to see how understand this. But let's move to see the validator side of this protocol. So I think that my time is expired, but in summary we saw different things about the beacon state. We find the Genesis times, Genesis validator, the slot things we will see in another video, and start to understand different ways of this beacon state. And you can see that any kind of protocol specification is so long because have a lot of implementation around all the protocol. But you can study with me in this seminar for understand the beacon state and all the protocols out there. So see you in the next webinar and have a nice day.